Hi everyone! Let's create a shader that looks like a simple radar, which can be useful for many types of games. It will be entirely generated using lines and other primitive shapes, and we'll add some animation to it as well. So let's get started. This time we'll generate an effect without a background texture, so I'll use a simple color rect in a new UI scene. As usual, I'll set the dimensions to Full HD and add a new shader material, like this. So right-click in the scenes, create new scene, its user interface, and let's call it radar. Yeah, that's enough. And right-click in the root node, add child node, adding color rect, and in the inspector, I'll change the color to black and expand layout transform and set the size to Full HD 1920 by 1080. Okay. And scrolling down to the materials section, creating a new shader material. Let's click it and add a new shader, which is type shader, mode canvas item, and the path will be, let's change it to shaders, and radar.gd shader is the name of the file. Okay, and let's click it again to open it in the shader editor. And as usual, I'll delete everything we don't need, so we'll only be left with the fragment function, deleting vertex and deleting the white. Control S to save. Okay, so as I said, we are creating a simple radar whose static part is based on thin lines, straight lines, and circles. So I'll start with functions that generate these required shapes. Okay, so the radar is circular, which means we can expect some rotations and similar things. I've used the function that creates a 2D rotation matrix many times before, and it's based on a well-known formula. It looks like this. I'll put it before the fragment function, and let's call it mat2 for matrix 2 by 2 rotate, and the argument is float a for angle, and now the usual calculation. Float ca is sine A, no, SA, sorry, CA is cosine, equals cosine A, and finally the matrix return mat2, which consists of two vectors, two CA, SA, and the second one is vec2 negative SA and CA. Okay, next we need a function to generate a thin line, whether straight or circular. This can be achieved using the smooth step function and parameters that I'll define like this. So let's continue. Float line with parameters. Float start, float thickness, and float dist for distance. All right, and it's simple. Return smooth step with the edges 0.003 and 0. Actually, you can use different values, but it's important that they are very close to each other. And now absolute value of dist minus start, and let's subtract the thickness. Okay, and that's it. As the last helper function, I'll add a simple formula for a filled circle, since several such shapes will appear in the final effect. So let's call it float fill with the argument float shape and float size. Okay, and this time it will be even simpler. Written smooth step with the edges shape and size, and let's apply it on just one. Okay, now we can start coding. I'll begin with uniform parameters. There won't be too many this time, but I'll still add them gradually as needed. First, we'll need the resolution for aspect ratio correction and two colors, one for the radar itself and another to highlight detected enemies. Okay, scrolling up to the beginning of the shader code and now uniform parameters. Uniform vec2 resolution equals vec2 and our full HD 1920 by 1080. We will need it for the aspect ratio recalculation, as you probably know from previous videos. And now the mentioned colors. Uniform vec3 RGB format, line color with a hint source color and the initial value vec3 0, 1, 0, which means we will have a nice green radar. Okay, and the second one, uniform vec3 enemy color as a hint source color to add the you know what, color picker to the inspector, and this time let's display them with a red color. But of course, we can change them in the inspector as we want to. Okay, next we move on to the fragment function, scrolling down, where I'll set up the usual structure. So deleting this comment, and first the radar is supposed to be displayed in the center, so we will move the coordinates origin to the center as well. Back to UV equals UV minus 0.5. Now the aspect ratio recalculation, uv.x is multiplied by resolution x divided by resolution y. And let's start accumulating the elements that will form the final effect. So float result is 0, and vec3 color is simply result times line color. So we give it the color defined in the uniform parameters, and finally let's display it color, which is vector 4 and consists of our color and 1 for the alpha channel. Okay, at this point we don't see anything yet because the result variable is still 0. So let's add something to it and start with the circles that form the base of this radar. But we need to know how many circles there will be and how far apart they are. So I'll introduce two new uniform parameters for that. So scrolling up to the uniform parameters, and let's add them. Uniform float ring count with a hint range, and let's start with 4 rings, and the range would be from 1 to, for instance, 5, and the step of course is 1. We don't want any fractional rings. Okay, and now the step, so uniform float ring step with another hint range, and I think 0.12 was the best default value, and it goes from 0 to 1 with the step 0.01. Okay, in addition to these parameters, it will be useful to know the center of the radar we are creating. We don't expect this center to change too much, so I can define it as a constant just before the uniform parameters. Const vec2 center is vec2 and 0, 0 in the center of our color rect. Okay, and now we can code. So let's get back to the fragment function, and first I'll define a circle using the length function right after the result definition. Float circle is simply length of UV minus center. Okay, I'll pass this result as a parameter into the fill function and set a small size because we want to create a point at the center of the radar, like this. The result is increased by fill of circle, and 0.01 should be okay. Let's wait for it. What's wrong? Result, blah, 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 fill circle. Ah, it's full. It's supposed to be fill, of course. Okay, and now we can see something. We'll immediately improve this result by adding circles using the uniform parameters. So let's get back and continue. For float I from 0 to our ring count parameter I++. So this is the cycle where we create the rings. A result is increased by line function I times ring step for the radius, 0 for the thickness, and circle for the shape. Okay, wait for it, and here we go. That's not bad. We can immediately verify how the ring count and the ring step parameters work in the inspector. So let's expand that, and if I increase, it's bigger, now it's smaller, and changing the ring step also changes the, I would say something like a zoom factor. I expect the point in the center, which remains always the same. Okay, notice that the actual number of circles is one less. It's just 3 and the parameter is 4. Because the index 0, for the index 0 in this cycle, we create an invisible dot in the center. I did it this way partly because the final circle, which forms the outer edge of the radar, will have a slightly greater thickness. I'll add it like this. So let's continue after this cycle, this loop. Float radius of the outer ring is simply ring step times ring count. Okay. And now let's add one more ring. So result is again increased by the line function applied on the radius. This time let's make it a bit thicker. So 0.003, and again the circle shape. Okay, and here we go. Let's just show more of that. Okay, so it's time to add the crosshair, which is typical for this kind of radar. And so that we can customize it to our needs, we'll need a parameter that defines its rotation angle. This time the value won't be in radians, but in degrees. Okay, let's add it here. So uniform float angle with a hint range, and let's start at 0 rotation. And as I said in degrees, so let's make the range from 0 to 180 degrees, and the step 0.01 can stay as it is. Okay, now I'll insert a function called crosshair inside it. We'll draw the two lines that make up this object. To achieve the correct rotation, we shift the coordinates to the center, apply the rotation by a given angle, and then shift the coordinates back to their original position, like this. So let's find the functions, and just before the fragment function, I'll add the function, as I said, crosshair. Float crosshair, and the parameters vec2 uv of the current pixel, vec2 c for the center coordinates. Now float thickness and comma, and float rotation for the angle. Okay, and now the rotation matrix. So mat2, let's call it simply R, is the result of our rotate function applied on the angle, but the trigonometric functions sine and cosine expect the parameter in radians, so we need to convert degrees to radians, and luckily the Godot shading language gives us a simple function called radians, which does it for us of the rotation in degrees, and the result is the angle in radians. Okay, and now let's do what I said, shifting the coordinates first. UV is UV minus 0.5, moving to the center. Then let's apply the rotation multiplied by the rotation matrix and shifting back plus 0.5. Okay, and let's do the same for the for the center. So C vector and C vector right here. Okay, and finally let's return the crosshair. So it will be two lines. Return line of Cx and thickness and UVx. This is the first one, the horizontal one, and now let's add the vertical one. Line C dot y, again thickness, and UV dot y. Okay, and the function is ready, and we can add it to the fragment function. Let's scroll down and find where we left before, right here. Result is increased by crosshair function applied on UV coordinates, our center, the constant, 0 for thickness, and angle for the rotation. Wait for it, and here we go. But it looks like our lines extend infinitely, so we'll clip them using a simple mask created with the step function. So let's just multiply that by the step function applied on circle and radius. Okay, wait for it, and this is perfect. Now we can try changing the angle in the inspector and rotating our radar. Everything works as expected. Okay, so the static part of the radar is done. Now we need to bring it to life a bit and add the typical pulsing effect, for which I'll write a separate function. It will be very simple and fit on a single line. So I'll write it first and then explain it briefly. Let's scroll up, and after the crosshair, I'll add a function called pulse. Float pulse. Now parameters float shape, float amplitude, float frequency, and float thickness. Okay, and to simply return another line with parameters amplitude times fract of internal time times frequency and thickness and shape. Simple as that. Okay, as you can see, the function does nothing more than calls the line function we already used earlier to draw circles. The difference is that the first parameter changes over time. This one. And this animation is controlled using the amplitude and frequency of the pulse. We'll set these parameters in the fragment function, where I'll now add a call to this function. So scrolling down, and after a crosshair, let's add this. Result is increased by 0.5 times pulse function applied on length, UV minus center, and radius, and now 0.6 and 0.0005. Okay, wait, and here we go. Now it's nicely pulsing. Notice that the color of this animation is slightly darker, which is caused by multiplying the result by 0.5. The amplitude is the same as the radius of the largest circle. The frequency is set to 0.6 and the thickness to 0.0005. Of course, you can convert all these constants into additional uniform parameters if you want to easily tweak them. So the radar scans the surrounding space, and it would be great if it could also display the position of detected enemies. To make it possible to send this data from a script in our game, we'll add 2 more uniform parameters and 1 constant. Okay, but I just realized it's not necessary to write this whole definition of length again, because we already have it right here, defined as the variable circles. Let's just change it to circle. It's shorter and better readable, and that's exactly what we want to. Very well, so the constant I mentioned, let's add it to the beginning of the script. Const integer enemy count, and let's set it to 3, for example. All right, and now the mentioned parameters, both will be arrays. The first defines which enemies are active and should be displayed. The second sets their positions on the radar. I'm adding it here, adding them here, a uniform bool in the with the enemy count size, and let's call it enemy active. Okay, and the second one, uniform float enemy count times 2, and the name is enemy data. Okay, it's twice the enemy count because we need x and y coordinate of every enemy object. Okay, you might be wondering why I had to define enemy count as a constant. The reason is that the Godot shading language requires uniform parameters of type array, these two, to have a fixed size known at the compile time. This is probably because Godot internally converts such arrays into separate parameters, so this limitation has to be considered. However, if displaying 3 enemies isn't enough, you can simply increase this number to the required maximum. And now their visualization. I'll create a function called enemy that adds a small pulsing circle to the scene along with a static dot at its center. Additionally, we want this effect to appear only inside the radar, not outside it. So I'm scrolling down back to the fragment function, and before it, let's add a function called enemy. Float enemy with parameters vec2 uv, float circle, and float radius. All right, and let's do it. Float c is simply length of uv minus center. Yeah, again, this definition, but if I don't do that, we would have to pass it as another parameter. Now float E for enemy is fill of C and 0.008 plus. So this is the dot, and now the pulse. Pulse of C 0.05, 0.7, and 0.0004. Again, you can change these parameters if you want the effect to look slightly different. And finally, let's return the combination. So E times step circle radius, which is the mask, and to ensure that the enemies won't be displayed outside the radar. Now we can add the code to the fragment function. Since these objects will have a different color, we'll insert them after the color definition. So let's do it here. For int I from 0 to enemy count I++, okay, and the cycle itself. So if enemy active, otherwise there is no reason to display it or do any other calculations. Let's calculate its position. Vec shift is vector2 of enemy data I times 2. This is the first coordinate. Now the same for the second one. Enemy data I times 2 plus 1. Okay. And let's add it to the screen. So color is increased by enemy function with UV plus shift to make it move. Circle in our radius, and let's give it the right color. So multiplied by enemy color. Something is wrong. Let's see what exactly. Vector representation circle. What exactly is wrong? Circle. Sorry. Comma, not the dot. Okay, now it's correct. But I found a typo here. It's not supposed to be I plus 2, but I times 2. Now it's fine. And we don't see anything yet because no enemy is active, of course. Let's find these parameters in the inspector and demonstrate how they work. So I am expanding enemy active, and let's activate the first one. Now we can see the pulsing dot at the center, and if I expand enemy data and change the first value, we can see how it's moving across the x-axis and now the y-axis. Okay, this is the first enemy. We can also activate the second one and move it elsewhere, and the third one, and do something else with it. Okay, everything seems to be working. Let's reset. Okay, of course, in practice, the actual parameter values will be sent from a script based on the situation in the game. So I'll add a simple script to demonstrate the movement of two enemies. Okay, so let's get back to the scene tree and select the root node, and I'm adding a script which is called simply radar.gd create, and here it is. So we'll need a reference to the color rect. So I'll drag this node into the script while holding Control key, which creates the full declaration. Now for the variables. Since I'll be simulating enemy movement using periodic functions, I need to know how much time has passed. This won't be necessary if you're determining enemy positions in some other way. So let's define var elapsed time, which is a float value and starts at 0. Next, I'll define an array containing enemy objects. In a real game, you'll probably have more complex objects, but here, a simple array of vectors is enough. This will store their projected 2D coordinates for the radar. Var enemies is an array of vector 2. Okay, and let's just initialize it as an empty array. And finally, I'll add variables that correspond to the shader's uniform parameters. So first var enemy active, which is an array of booleans. And again, let's just initialize that. And the same thing for the enemy data. Var enemy data is array of floats and empty array. All right, let's continue with the ready function, where we'll perform initialization. I'll start with just a single enemy object. So enemies append simply vector2 0. Let's add it to the center of the radar. And now we need to activate the arrays. So for enemy in enemies, enemy active, let's append true so we can see something. Enemy data, append our enemy x coordinate, and the same for the y coordinate, enemy dot y. Okay, The actual animations will take place in the process function. Process. Here, I'll recalculate the enemy's position and send updated parameter values to the shader. So elapsed time is increased by delta. And now correct. Crap. The variable, of course, material property, set shader parameter, and the parameter name is enemy active, and the variable is enemy active. Okay, now the recalculation. Enemies 0, the first one. X is sine of elapsed time times, let's say, 0.5 times 0.4. So this is a simple function to simulate something like a circular but little irregular movement. And let's do a similar thing for the y coordinate. Enemies.y is cosine elapsed time, and this time let's give it another frequency and amplitude, 0.7, 0.3. Okay, and now the actual animation in the shader for index in enemies size. Let's send the data. Enemy data. First fill the array, then we'll send it. Index times 2 is enemies of index and the x coordinate. Now let's do the same for the y coordinate. So it's index times 2 plus 1 is enemies index dot y. And finally, let's send it. So I'll just copy this line and change the parameter. Set shader parameter enemy data, but of course we want to send it just once, so let's move it outside the for cycle. Okay, and we are done. When I run the scene now, let's do it. We can see, we can observe a moving object that our radar has detected. Notice that sometimes, right now, sometimes the object flies outside the radar and disappears for a moment. That's exactly what we wanted and why we added a mask in the code to ensure this behavior. Let's exit the scene. Okay, and we can also show how easily we could add another object that moves more slowly and along a slightly different path. So let's get back to the ready function and duplicate the first line. So now we have two enemies in the array. And in the process function, let's just copy and paste these two lines and change the index to 1. So we are working with the second enemy, and let's change the values 0.2 and 0.6, and here for example 0.4 and 0.1. Let's start it again, and we should see two dots with different trajectories and different speeds. Of course, in a real game, enemy positions would most likely be recalculated elsewhere in the code, and the script would simply receive a ready-made array for the shader. Let's get out of that. The exact approach depends on each programmer's preference. Thank you very much for watching. As you can see, this is a very basic type of radar that could be improved in many ways. For example, each enemy could have its own color. We could add numbers or labels to them, highlight the one currently targeted, and so on. Maybe there will be time for these extra features in the future. And once again, I'd like to remind you that the full shader, including the script, can be found in the Godot shader pack, which I've linked in the video description. For now, take care, good luck with your projects, and see you in the next video.